Good evening to all. Welcome to our International Physics webinar. And this is the first webinar of this new year, 2023. And I hope many more will come in this one first. Today, the title of this webinar is Peering into the Darkness, Black Holes in the Event Horizon Telescope Era. And our speaker is Professor Sera Markoff from the University of Amsterdam, Netherlands. And she has already connected with us. So I'd like to welcome her. So, Madam, good afternoon and good evening to here.
Yeah,
And
hi
thanks for
everyone.
accepting our invitation, Madam.
Okay.
So, before going to, I'd like to introduce you with our viewers. So, today our speaker is Professor Sera Markoff, and she is currently working as a professor of theoretical high energy astrophysics, Anton Pannekoek Institute of Astronomy, University of Amsterdam, Netherlands, and she worked at the interface of astrophysics and astroparticle physics, and she is also interested in a variety of problems relating to the accretion process, especially around the black holes, both big and small. And she is a member of the Event Horizon Telescope project, and where she is currently working as a vice chair of the Science Council and the Cherenkov Telescope Array project. We can see she has completed her bachelor degree from MIT, USA, and her master's degree in theoretical astrophysics from University of Arizona in 1996. And she completed her PhD in 2000 in theoretical astrophysics from the University of Arizona. And her thesis title was High Energy Process in Galactic Center. She started her research career, as a undergraduate researcher at the MIT Center for Space Research, and her thesis was the unusual Rosette quasar. And then she worked as a visiting graduate student researcher at the Roka Institute of Physics, Hebrew University, Jerusalem, Israel. And then she worked as a graduate student researcher at the University of Arizona, and she worked there up to 2000 from 1994. And then she also worked as a Humboldt Foundation Research Fellow from 2002 to 2022, uh, and also work as a National Science Foundation Astronomy and Astrophysics Postdoctoral Fellow, MIT, USA from 2002 to 2005. And currently, she is working as a professor of high energy physics, theoretical high energy physics of University of Amsterdam. So her actually research interest, accretion and outflow around the black holes of all the mass scales and the relationship between them, as well as their impact on their surrounding environment, high energy astrophysics, astroparticle physics, multi-wavelength astronomy from low frequency radio through gamma rays, and instrumentation, also the global millimeter VLBI project, Event Horizon Telescope, and next generation TeV gamma ray facility and Cherenkov Telescope Array. So I think you will enjoy this session. So, Madam, thanks again. It's your time. You can start your session.
Okay. Thank you so much, Pretam. And thanks. I can't see anybody, so I don't know who's out there, but I hope you're having a nice evening. Thanks for joining later than usual. So I've never been to Bangladesh. I wish I could go in person maybe someday to visit, but for
Yeah,
now
I'll
I'm
happy
there
to invite you, Madam. It will be a great
next
honor for
time.
me, of course.
Would like to. Basically, I've tried to aim this level for people who have done, are working on their bachelor's in, physics, and maybe some astronomy, astrophysics. I believe there will be time for questions. If you have urgent questions during the talk, I think there are channels that you can ask, and they will be, and Dr. Pretam can interrupt me. But anyway, so what I wanted to talk about in a general context is these first two pictures of two supermassive black holes. These are direct images of them taken by the Event Horizon Telescope, or I'll often say EHT for short because it's quite a lot to say. Now, as Pretam mentioned, I'm a member of the collaboration. I actually am no longer on the Science Council. I finished my terms from that, but within the collaboration, I also help contribute to the modeling of these and interpretation of these data sets. And I also help coordinate what's called MWL, stands for multi-wavelength, the multi-wavelength working group, where we try to coordinate our EHT observations with other telescopes around the world, also in space and on the ground. And a little bit later in my talk, I'll explain why that's important. But so I just want to mention that when I talk about the results of EHT, I'm representing the work of over 300 people in the collaboration. This is a real team effort that's quite global. And then sometimes along the way, I'm also going to talk about or show some images from work in my own group, mainly to illustrate some ideas. But I just want to point out that I always put the names of younger people that led the work in my group, from students and postdocs, present and past. You can see in orange here. You'll notice that one of them has a nice Bengali name, you know, is from originally from Kolkata area, and that was my recently graduated last year PhD student, Kaushik. So you'll see his work along the way as well. But anyway, anytime you see these orange names, that means it's a young person leading the group. So I'll start by introducing you to these two black holes. Now, I'm hoping probably you've seen these pictures. You know, they were quite big on like social media. But what you're seeing on the left here, this is the supermassive black hole, which is in the center of the M87. That's where the name comes from, M87 galaxy. We use this little star here and we pronounce it M87 star. And that's a way of distinguishing between the galaxy, and then when we're talking about the black hole, we talk about this little star. That's a historical thing that actually came from this one, but I'll mention it first. This is a huge black hole. It's one of the biggest ones that we've ever, that we know of. It's 6.5 billion times the mass of our sun. So it's basically, in terms of the size of the black hole, which is linear with the mass, it's about the size of our solar system, to give you some idea. And this result was presented for the first time, the first ever picture of a black hole in April of 2019. And then we presented just this past May last year the results for our own galactic center, our Milky Way's black hole. And you would think, that it would be called Milky Way star or something, but because of historical reasons, this source was discovered in what looked to be the Sagittarius constellation on the sky. And so it's called Sag for Sagittarius, and then in this complex A. So Sag A star is the short name for this. And you can always tell the difference between them because Sagittarius star is kind of clumpy looking, and M87 has this very smooth, bright ring on the bottom. It's a much smaller black hole in our galactic center. It's a smallish one overall, kind of a moderate one in terms of all the black holes in the universe. It's about 4 million times the mass of the sun. And it's much closer, though, so it looks to be about the same size in the sky. And that's not a coincidence. It's because we have a specific telescope that can only see things within a certain size. So these are the two kind of Goldilocks black holes that we happen to be able to see with our telescope this way. And we can't really see any others at the moment. So I'll say more about that later. But, if you just looked at these pictures and you didn't know really what you were looking at, I don't think you'd be that impressed, right? I mean, they're kind of fuzzy. We have much better pictures from Hubble telescope and now James Webb, the JWST. But it's a pretty amazing story that we managed to get to the point where we could make images like this. And so I want to spend the first part of my talk actually giving a little bit of historical background about how we got to the point of being able to see these black holes in the first place and think about black holes in the first place. And then I'll say a bit more about the context. Why are we interested in black holes? What are we trying to learn? And that way I build it up to the point where it makes a little bit more sense when I'll come back to actually presenting the results of EHT and put them into context. And then depending on the time, we'll see, I'll say a bit more about kind of what's coming, but we'll see how that goes because I want to make sure there's some time for questions. Okay, so let's start with a bit of context. And I always like to think a bit about history because it's kind of amazing if you think about it that, humans have been walking the earth and sort of conscious, depending on who you talk to, but roughly, hundreds of thousands of years. And yet we really haven't understood our universe in a more fundamental physics way, except for the last, roughly 100 years or so. And so, if you think just before 1915, at the sort of turn of the century, before the last century, there was, people didn't really know what the fundamental forces were. They knew something about electromagnetism, but quantum mechanics wasn't really there yet. There wasn't really this understanding of carrier particles, or even which particles existed yet. Many particles hadn't been discovered. And we didn't even know that we lived in a galaxy within a universe of galaxies that are expanding away from each other. This was all not, all of this was coming. And if you had gone up to the average, physicist on the street and you said, hey, guess what? We're all living embedded in some 4-dimensional space-time where you have the 3 dimensions of space, which is what you, experience every day. But time is actually linked to these. And it's this kind of fabric that if you have something very massive or very energetic, it can actually warp this fabric of space, will force things to move in directions that maybe aren't even straight lines. And you will think this is a force called gravity, but it's actually a byproduct of, space-time being warped. And I think most people at the time, rightly so, would have probably thought that was a bit crazy. And in fact, when Einstein first came out with this theory around 1915, general relativity, a lot of people did think it was kind of crazy. It was very radical at the time. But what's amazing also to think about is this was during a war. It was actually the first big world war. World War I was started in 1914. Yet, people were still managing to do this work. And somehow, some guys, this famous Lord Eddington was, apparently wealthy and privileged enough that during the war he could arrange a vacation down to the Caribbean, where he could test with a group the prediction that light should be bent around the sun. And he looked at this during a solar eclipse, and they proved that Einstein's idea was right. So basically, in his own lifetime, within just a few years, Einstein was already becoming quite famous. And that's actually quite rare for scientists. Many people, you have to wait a very long time to go from theory to actual proof of theory. So it was a special moment. But even before general relativity was proven, many people were thinking just about the interesting mathematical implications of this, of space and time. And some of you might have heard of Schwarzschild, because we now refer often to the event horizon of a black hole as the Schwarzschild radius. So he was thinking about the solving Einstein's equations in the special case where you have a spherically symmetric object, like a star. But he wasn't really thinking about actual astrophysical stars. He was just sort of thinking about just a case study. And interestingly enough, the one you haven't heard of was somebody doing this exact same thing completely independently, named Droste. He was actually a grad student. He was a grad student of a famous physicist in the Netherlands called Lorentz. But, as things often happen, when you have a big famous guy who comes up with a theory at the same time as a student, people often will remember only the more famous one. So I think it's nice historically now we're starting to think a bit more about giving credit, to people who contribute to the work. So these two guys were thinking about this, and their mathematical formalism predicted that something kind of funny happens in the math, that there's a radius that within which, if you send something within this radius, like a signal or anything, it can't escape. This is the thing that became called the event horizon. It didn't really have a name at the time because nobody thought it was real. For a normal star, it would be way inside the surface, and it just seemed like a mathematical curiosity. It didn't seem like a real thing. But that didn't stop people from thinking about it, because it was kind of an irresistible problem. And that's what physicists like to do, is, think about fun things. And so there were some famous mathematicians and physicists like Dave Hilbert and Max von Laue already in the, a few years later. Now, if you look at this is basically telling you everything you need to know about our image. This is from the 1920 paper. I mean, I think this is someone's like coffee stain or something from the book, but it's ray tracing diagrams. So what you're seeing is imagining that somebody over here is shooting photons at an object that's inside its own event horizon. And if a photon starts to get bent by the space-time, so it should have passed by, but it gets focused onto the surface and then it disappears. So you won't see that photon anymore. But if you shoot this photon, same thing happens. It gets bent by space-time and it hits the surface and it disappears. But there becomes a point where if you go far enough away, we call this the impact factor, there's sort of one critical distance where you hit the photon, you send this photon, it gets bent by space-time, but it just sort of skims this region, and it can actually, in fact, go around many times, hundreds of times, millions of times, and eventually actually escape because it doesn't go into the event horizon. And then if you're sitting out here, what you're going to see is the photons that get focused by the black hole but then escape, or the ones who don't actually get near the black hole at all. Of course, this, at the time, they didn't know this was a black hole, so I'm kind of jumping the gun. But that tells you everything you know about our image. And so we made, oh, and actually, let me say one more thing before I forget, that because this, what you see is that the size gets expanded, you know, basically, this is what we call gravitational lensing, that gravity bends light, but just like a lens from glass, it can actually, you know, make images look bigger. And so what happens is, if you're looking at this from infinity, you'll see light from around the sort of shadow of the black hole or this object would be 5 times bigger than its event horizon. So it expands it. Now you're going to see a little movie, and I hope this works also on the platform. But this is showing ray tracing diagrams. Again, now you can see light coming in. It can bend around the black hole. Most light in this image are coming from behind, but it doesn't actually matter because the light can come from any direction and this will happen. So what that means is that no matter where you are, if you're looking at a black hole, you would see the same thing. If it's somehow lit up by a light source, no matter where the light source is, and no matter where you are, you'll always see a ring of light that's from this light being focused around the black hole and some light being absorbed. And then this is more or less what you're looking at when we look at our images. And it's a little more complicated than that, but I'll say more about that in a second. Now, of course, as I said, at the time, people did not think this was real. They weren't really thinking that far in advance. And they didn't, you know, certainly had no name for such an, you know, kind of absurd idea. Eventually, people started to think that there could be stars that might actually collapse inside their own event horizon. That idea started to come in the 30s and 40s, and people started to think that maybe these things could actually exist. And by the 60s, people were actually starting to find detections of the first black hole candidates, for instance, small black holes, which are the remnants of stars in the galaxy. The first real candidate was one named Cygnus X1. I won't say too much more about the history there, but the point is that at some, you know, point in time, if you really think something exists, you need to have a name for it. And before, people were talking about this theory as gravitationally completely collapsed stars. And it was really hard to say. So how did it go to actually having a named black hole? And I think this is a bit interesting, especially because given that this all took place about a day drive, a long day drive from where you're sitting. I looked on Google Maps. But it actually has a colonial history. And I think a lot of people don't know this story. So I think it's worth telling. So John Wheeler was a famous physicist. Many of you might have heard him say things like black holes have no hair. This was something he came up with. He said to basically say that, you know, black holes, other than their mass, their spin, and their charge, don't really have any distinguishing features like people, you know, with hair. So that's a pretty famous statement that we use all the time in physics. So he was kind of a marketer. He was good at coming up with catchy things. And he was giving a talk in the 60s when people really started to believe that something existed like this. And he was complaining in the talk, I don't really have a good name for this. I keep having to say this long thing and I need a better name. And this guy, who was a British scientist, but this was happening in the US, I think at New York at the time or something, but he yelled out, what about black holes? What about the idea of black hole? And Wheeler thought, hey, that's really great. And it's such a good name for the concept that, you know, this sort of dark thing, light comes in, doesn't come out, kind of a bit scary. But where did the name come from? And it turns out that in the 1700s, as you all probably know, the British were trying to establish rule in India and surrounds. And they had, there was an East India Company had a garrison in Calcutta. And it was, you know, a bunch of soldiers, and they were trying to establish rules. So if anything happened they didn't like, they built a little prison and they would throw locals into it. And they called it the black hole because it was dark and not a nice place to throw people into. Eventually, the locals didn't really like this very much, understandably, and they rebelled and they won. And they threw all the British garrison, I think there was almost 200 soldiers, into this prison that was actually designed for something like 10 people. And they mostly died. And this was actually, you know, drawings were made. This was in the newspapers back in England. It was a very, you know, traumatic event for the British to have something like this happen, but it made its way into the lexicon. People started to say the Black Hole of Calcutta, and they would refer to this prison. I haven't seen it, but I heard that there's a plaque somewhere where you can find this. So if any of you go there, tell me. I want to find where this is. But so Robert Dick, growing up in the UK, had heard this expression, had used it occasionally, but you know, putting it together with an astrophysical object is kind of how this all happened and during a talk, according to, you know, the historical stories about this. I think that's kind of an interesting thing. But anyway, the name has, of course, really resonated with people. Most people on the street know what a black hole is, which is kind of incredible when you think about something that is such an abstract concept. And I think it really has a feeling, you know, I think the fact that it has a bit of a scariness to it, and the fact that it has a little bit of a scary, sad, you know, historical background puts all these things together. So I quite like telling this little bit of a story. But here we are now, and we live in a really amazing time. I mean, you as students, if you think about it, you're coming into a period of human existence that we just didn't even have like more than, you know, 7 years ago or something, 8 years ago, because we now can actually see the ripples in this fabric of space-time called gravitational waves. And we can see the unseeable. We can see black holes, not exactly, but we see them via the light that is emitted around them. So there's a lot to do and a lot to learn and a lot going on. And of course, I can't tell you everything about it, but I think it's nice to know a bit about why we're interested in black holes. What are some of the questions that, you know, someone like me, I'm an astrophysicist. I try to understand black holes and their role in the universe. What do they do? Why do we care? And that won't be the same reason for everybody, of course. But, you know, then there's people who are more on the theoretical physics side who want to understand really what is the nature of space-time? What is it that black holes do? And we work together because we can't understand this problem without, you know, in some sense, we have to separate out the astrophysics from the general relativity and know which is which. And as I'm going to show you, there's quite a bit of confusion there as well. So let's start with this idea of what black holes do. Now, we think, and we've pretty much established this by now, that almost all galaxies have a supermassive black hole in them, at least, you know, maybe sometimes even more than one if they've merged. I'll come to that in a second. But typical galaxy, like our own, has a black hole in the center. And we can't zoom out and look at our galaxy. But if we could, it would look something like this. So this is actually M81. It's a proxy, very similar to our galaxy. It's a spiral, grand spiral. And a lot of people think that black holes, you know, will eat the galaxy, or maybe they're holding the galaxy together. So it's important to remember that most of the time, black holes are what we call dormant or quiescent, and they don't really do very much. So we think that the black hole forms together with its galaxy in the early universe. We're not entirely sure, you know, how this happened. There's quite a lot of debate about this, but they seem to grow together. I'll come to that in a second. But when they're dormant, the black hole really can only influence a pretty small region around it where its gravity is felt, and it can pull things in and win out over other forces or other things pulling things away with gravity. And that turns out to be very small compared to the galaxy. So the reach of a typical sort of black hole in the galaxy is something on the order of about 100,000 times more than its own event horizon. And that sounds pretty big, but if you put that on a figure like this, for instance, our own Milky Way is about 500,000 times larger than the reach of the black hole Sagittarius star. And so if I put it on this figure, you wouldn't even see that, it'd be a tiny little dot. So you can get a sense that the black hole is kind of insignificant, other than very close by. It has a lot of gravitational influence when it's dormant. And from our point of view, we live out here somewhere in the suburbs. We don't feel the influence of the black hole at all. But something has to be happening sometimes, because here's a nice picture of the deep field from JWST. So this is basically if you took a grain of sand and held it at arm's length and looked at the sky, this is what you would see sort of behind it. And there's thousands of galaxies in this image, and each one of these has a black hole. Some of these you can see are distorted, and that's called gravitational light bending or lensing, just like we're talking about happening around the black hole from light coming nearby other heavy galaxies. But if we measure the mass of the black holes in these galaxies over orders of magnitudes and then plot that against, this is a proxy, it's called sigma, but it's basically telling you about how fast stuff moves around the center, and it's a proxy for the mass of the galaxy. What you see is that over orders of magnitude, over many different kinds of galaxies from small to large, there's a very tight relationship between the mass of the black hole and the mass of the galaxy. So what this means is they have to know about each other. They have to regulate each other in some ways. They have to grow. But if the black hole barely talks to the center of the galaxy, this tiny little region, like we looked at in the last image, how does the rest of the galaxy know what the black hole is doing? If the black hole decides to grow, how does the galaxy get affected and say, hey, I've got to grow? Or if the black hole, has to stop the growth, how do they talk to each other? And that means something must happen that's different sometimes. And we call that activity. So what happens is the black hole, for some reason, will be able to capture more material at different times. It becomes what we call an active black hole. And then it becomes very dramatically different. And the best way is just to show you. So this is what we call a multicolor or a 3-color image, where we've combined images from 3 different types of telescopes, some from the ground, from space, into one image. And we've translated colors we can't see with our eye into colors we can. So it's kind of what we call fake colors. So the colors mean nothing. But what you see here, all the whites, is basically, actually that color means something. That's from Hubble. And that's basically what you could see with your eye. So this is the optical image. And all of these things here are not stars, but are actually other galaxies. So you're looking at a cluster of galaxies. It's the largest bound structure in the universe, and basically gravitationally bound structure. So you have all these galaxies kind of growing together. It's like a nursing ground for galaxies. And in the center, you have one really big galaxy, and this galaxy is in the active state. And when it's active, often what happens is it's launching these enormous jets of magnetic plasma that are launched at nearly the speed of light. And that magnetized plasma gives off a kind of light that's called synchrotron, coming from charged particles moving in the magnetic field. But that emits radio waves. And radio waves you can't see with your eye, but we've translated that to blue here. So you see, these things are enormous. The galaxies, here, this thing goes way beyond the galaxy, out to, basically 1 billion times bigger than the black hole's event horizon. So there's no problem communicating not only to the galaxy, but actually to this whole breeding ground. You can actually have black holes, when they're active, can affect the entire surroundings. And in pink, we see the X-rays from Chandra in this case. And that's a telescope that's in space named after Chandrasekhar. And what you have is all this gas in between all these galaxies has basically been heated to the point where, like the solar corona, it can emit, X-rays, very energetic. And we find that, in fact, the amount of energy being dumped into the surroundings by a single massive black hole in this case will actually be on the order of hundreds of billions of supernova. So it's one of the most energetic processes, the most efficient conversion of energy that we know of, more efficient than nuclear fusion, actually, when these things are happening. And so we think that via these jets, for instance, and other kinds of outflows, the black hole manages to have a feedback effect on its own galaxy, on its other galaxies, because if you heat gas, you basically keep it from forming stars. And so galaxies can no longer grow when the gas gets too hot. And this way, the black hole can actually start to kind of make a feedback cycle. So this is why we're very interested. We're trying to understand, how these jets are launched. So now I'm going to start coming into, okay, so here we are. We've got 2 very different galaxies, but the black holes look pretty similar to each other, all things considered. However, they're in very different environments. We have Sagittarius A star, our Milky Way. This is, again, the proxy M81. But this is a pretty small galaxy, a small black hole, and it doesn't seem to be in this active state. There's no big jet that we can see. Meanwhile, M87 is a huge elliptical galaxy. It's got this big jet that's clearly active right now. It's actually punching through the entire galaxy. And the root of this is being launched, right outside the event horizon. So if we want to understand why is it that sometimes black holes go into these cycles where they become active when they're dormant, why are jets launched, what's inside them, how does this feedback work? These are the perfect set in some sense. We have an example of each kind, and then we can use the Event Horizon Telescope, maybe together with other facilities, to try to understand these questions. One difference might be the fact that this one is a very powerful, M87 is a very powerful black hole, and when it's active, it's giving off the power of billions of suns, whereas in this quiescent state, Sagittarius star is giving off basically the energy of like 1,000 suns at most, so it's not very energetic. That could be one of the reasons, but we're looking into this. So that's kind of the background of where a lot of this is going. And we also want to understand, when galaxies merge, they form bigger galaxies and then their black holes merge, and we think that that may play part of the role here as well. And again with JWST, but here's 5 galaxies that are in the process of merging, and we could see that the black holes become activated and actually start emitting jets and so on. So there might be some relationship there that kicks this off as well. But at the end of the day, we don't have a theoretical model that really predicts what comes out of a black hole as a function of what goes in. So we're kind of guessing a lot of the ways of what's happening, and that's why the Event Horizon Telescope is so important. I'll just mention also that some of you may be familiar with the Large Hadron Collider at CERN. This is the largest particle accelerator on Earth at the moment. And we can get particles up to about 13 TeV, 13 TeV, which is about 10 to the 13 EV. This is, seems like a lot of energy, but if you compare to these jets, which are huge particle accelerators, we can, in outer space, accelerate particles up to, millions or tens of millions of times higher energy, and in fact, probe new physical regimes. So we also want to use these black holes to understand particle acceleration in ways that we can't really study on Earth. And so there's a lot going on there as well that I'm kind of interested in, but I won't say too much about this. I'm mostly going to focus on EHT. Okay, so I hope that was, of course, a kind of fast trip through some history and some background, but let's talk about the project itself. Now, we're over 300 members from over 80 institutes across something like almost the entire globe, also where the telescopes are located, but also the institutes. So during the pandemic, it was very difficult. We had to move to mostly meeting online. We were having telecons at like 4 in the morning, 1 in the morning, trying to rotate like the pain through the time zones. We're finally back to sort of meeting in person again. But it's been keep in mind that all the work done, particularly for Sagittarius A star, happened during the pandemic. For the second black hole. So that was a really kind of a challenging time for everybody, especially a lot of the young people in the collaboration, because they couldn't really meet with each other and network and so on. So it's been interesting. And I think with that in mind, it's even more amazing that things really came out as good as they did. So what made people think, let's do this? Why would you think you could look at make a picture of a black hole? And so first of all, you could think, well, how big would my telescope need to be? So we already know from theory, we just said that the diameter would be 5 times the event horizon. And if you know the mass of the black hole, you know exactly how big the event horizon will be, because there's just some physical constants like the gravitational constant in front of it, and then the speed of light comes in there as well. So if you know the black hole and you know the distance of the black hole, you can predict what the angular size on the sky will be of the horizon. And then you could say, how big does my telescope have to be? And I'm sure most of you know, oh, actually, wait, I should just say, so, okay, right. So the prediction is Sagittarius star is, with 4 million solar masses and, distance of about 8,000 parsecs, the size would be 50 micro arc seconds on the sky. And that's 1,000 times smaller than what a space telescope like the Hubble telescope can see. And to give you some sense, I gave a talk recently and I'll put that number in there as well. But for M87, which is a much bigger black hole, it's also much further away. It ends up being a little bit smaller on the sky, like 40 microarc seconds. So this is equivalent where Utrecht is near Amsterdam. So it's basically saying that like from Utrecht or Amsterdam, reading a newspaper or looking at the head of the pin across the ocean in Boston. That's the kind of resolution you're talking about, or like seeing an apple on the moon or something like that. It's very, very precision. It seems almost impossible, but you can predict that if you know the wavelength you want to look at and then the size of your telescope, you can figure out your resolution. So let's say, what's the shortest wavelength? We want to make this as small as possible. So we want the shortest wavelength we can do this with. And the only way we can do this technique on large distances I'll come to this about making a sort of virtual telescope by connecting arrays is in the radio bands for the most part. And so we go to the smallest wavelength in the radio, which is in the millimeter. And then, if we want to get to something like 40 microarcseconds, then we have to go to about 5,000 kilometers. Now, the Earth is 12,000 kilometers in diameter. So if we really want to be able to probe some structure, we'd like to get down to 10, 20, microarcseconds. But we already have to go to a telescope that's bigger than the Earth if we want to get down to 10. So to get somewhere like 20, which is about what we got, we can use the Earth size. Now, I mean, of course, we'd love to build a telescope the size of the Earth. It would look something like this. Telescopes, the classic optical way is that you have a mirror and you focus the light from the black hole into one, focal plane where you have your camera or your your CCD, and you make an image. That would be, I think, not very cost effective, and it would also be very unpleasant for the people living under the telescope on half the globe. So it doesn't really work that way. What we do is a kind of a cheat where we can say, let's build smaller telescopes across the Earth. We can effectively use the separation between the telescopes as a sort of what we call a baseline, as a sort of virtual size of a telescope, but only in one direction. And then we can use a computer to collect all of the data. And this is a technique called interferometry, and a specifically very long baseline interferometry. And then, the question is where to put these telescopes. So we know we want to do it in the millimeter. Well, a lot of stuff at high energy doesn't make it through the atmosphere for good reason, because it would be bad for life. Then we have radio, we can already do easily from the ground. If you sort of look at the cloud cover, there's a place in between where millimeter is. And millimeter you can do from the ground, but you need to go to high and dry places because the atmosphere, water vapor is very bad. It basically absorbs millimeter light. So you have to go to high, dry places, very special places. There aren't that many. So one of the things we did was we weren't going to build our own telescope, but we actually joined telescopes that were already existing to see if this was even possible, because it was done for a long time in the low frequencies, but no one had ever tried. It's much harder because what happens is you have to basically collect all the data locally, time tag each photon wave, basically, put it on disk, and then combine it in a supercomputer later. And the technology also wasn't really available to do this, nor was there good storage. So everything had to be right. You had to have the technology. You had to have also the idea of what you were actually really going to be looking at. And so, the idea, you're not going to see maybe this perfect idealized ring, but like what happens if you've got a very, like in this case, microscopically thin disk around a black hole. And this was already thought of in the 70s. So I know that you've probably seen Interstellar, and they claim that this was the first time that anybody had thought of what things look like around a black hole. But that's obviously not true, because this was in the 1970s. People like Luminet were predicting, and this was sort of a contour plot of the light bending of a disk around a black hole. And then they didn't even have vector printers back then. You couldn't just print a PDF or whatever. So this guy actually did it by hand. He translated this contours into a paper drawing, and it was quite famous at the time, but then everyone forgot about it because it just, again, didn't seem quite relevant. It was only when people started to do more modern computer simulations, could actually simulate what you might actually see with an actual telescope, which was done in this paper. And you can see it's a pretty, compared to what we do today, it's actually pretty primitive, even though it was just 20 something years ago, because things go very fast with computation. But it was the combination of theoretically thinking we might actually be able to see a shadow. But there was a risk involved, because sometimes you might actually not see the shadow because the stuff around the black hole is so thick that you can't see through it. So you almost need to have the right conditions as well as the right size black hole. And so when the technology became available, people started to think, let's try this. And it was Shep Duelman, who was actually leading the team at the time, who really did the first prototype. He became the first director of the EHT, and tried to string some telescopes together in Hawaii and California. and showed that you could actually get a signal, because you need to basically get you collect the data locally, and then you need to get the delays and everything done perfectly that you get constructive interference, and you can actually see something. So that was the beginning of the EHT, and it's kind of amazing to think that the actual project began then only 8 years later in 2016, and then in 2017 took our first data, and that's the data that we've published so far. So it went extremely fast for astrophysics. Most like space missions or things like this take decades to go from concept to building, but this was very much like piggybacking on existing technology and borrowing other people's facilities. And so to think about how this was done, now, if we can see the black hole can see us. So let's put ourselves in the position of a black hole and looking at the Earth. The way interferometry works, it's not like a normal optical telescope, but what you're doing is effectively taking a Fourier sampling of the light pattern on the sky. So every pair of telescopes gives you one baseline with a distance between them. That distance sets the scale in this lambda over d resolution. So very large baselines probe very small sizes on the sky, and vice versa. So the smallest baselines we have on Earth will tell us how big we can see, and the biggest baselines that we have will tell us how small we can see. So we have a kind of limits of what we're able to make images of. That's a very specific thing to radio astronomy. And so here you have the baselines here, and you see you only get one, and that gives you kind of ratty data. Ideally, you'd want to have this whole plane filled out with as many baselines of different sizes as possible to sample the image on all the different size scales. But what we mostly see here is that we've got different baselines, and then we use, as the Earth turns, the projection of the baseline from the point of view of the black hole maybe is a bit smaller or bigger, and so we can use that to fill out what we call the UV plane, which is a parameter space. So this is now showing you a bit more complicated. This is that same movie again, showing you the baselines that we had in 2017. This is what's called the UV plane, which is basically the Fourier plane that's showing you the distance between the telescopes in giga wavelengths. It's a kind of a strange unit, but the thing to remember is that the more dots you see as the Earth turns and more baselines, a perfect Earth-sized telescope would just fill in this entire thing with color, and that would give you perfect resolution. But we have very sparse sampling. This will be the raw data here, showing you the amount of light coming out at a particular size scale. So it's basically the Fourier transform of the light pattern on the sky. And down here shows you 3 different ways of reconstructing the actual image based on the data we have at the time. So with one baseline, you can't really construct anything. But as the Earth turns, you start to see more telescopes. You start to fill in this sparse sampled space. You start to add more data here. And eventually you add up all the data. You really need to add everything together when you don't have that many telescopes. And then you can see that we got 3 different kinds of reconstructions. The uncertainty in the reconstructions, this one's a little fuzzier and thicker, and this one's a little thinner and more lumpy. That's the uncertainty and the limitations of our sparse sampling and image reconstruction. We can't do better than this. And so that our final image was basically adding up these independently made by teams that didn't talk to each other to give us confidence in the results. And then we make the final image from that. And then the fuzziness is kind of a measure of our error. So I hope that gives you some sense of, how we collect this, and I'll come back to that. But it's interesting to give you a sense also of the fact, I say, we're living on borrowed time. Our annual campaigns are really difficult. We don't own these telescopes. We're basically begging for time. Every year we have to write proposals to get the time for a couple weeks over the whole year. And so we're competing with other groups, and it's quite stressful. And to give you some idea, we're going to be observing again in spring in a couple months. And this time they didn't give us time on M87. They just said, you've got enough, work on your data for now. So we only got time on the Galactic Center. We don't always get what we asked for. In 2017, we had 8 facilities. We didn't have the Greenland telescope at the time. Then in 2018, we added in Greenland telescope. 2019, we had some technical problems. 2020, of course, we had the pandemic. So we lost 2 years. We had new telescopes again in the array in 2021, 22. we've only been analyzing, we're starting to, hopefully in the next couple of months, we'll publish the results from 2018. We've only published from 2017 till now. And then we're also slowly getting up to the newer data sets that we have, which are actually incredibly good, but we have to do things in sequence, and it takes a long time. And then each campaign is a couple weeks where we observe over, maybe 7 to 14 nights, and we only get like 5 nights or something. And we have to try to line up with all these other facilities that also look in the X-ray and the infrared. I'll show you why we do that in a little bit. And so we end up with this kind of crazy, we call it the Sudoku, trying to, here's like, some of you might know TeV facilities like Hessen Magic. These are other VLBI networks at lower frequencies. This is X-ray missions. And then every night we sort of make this table of like, what do we have time on? When is the time? And then we look at the weather and we try to decide if we can make things line up, but it's very stressful. So that was some years ago. Now we've gone to full spreadsheets with color coding, and it's gotten like really complicated. And we have to have this very stressful go, no go decision every night, just hours before the observations. And if, we can't tell a big space telescope to change its schedule at last minute, so we can spend all this time getting, a big space telescope ready to look at the black hole at the same time as us, and then suddenly it'll be cloudy and there's nothing we can do about it. And there's too much, snow on the dish or something like that, and we lose that time. So it's very challenging for us. And many young people are going down and actually operating these things during the campaigns. And then finally, as I said, you record everything digitally, have to pack it physically onto actual disks because you can't transfer petabytes of data by the internet. And then you put it on airplanes, you fly it to these supercomputer correlators, one in the US, one in Germany, and then they look at this mess of signals that has to be calibrated, and they have to find the right, delay to basically get the right phase and suddenly see the constructive interference, which is where you get your images out of, and finally make an image. Now, I want to say a bit more now about how we interpret these images, right? Because making the image is not the end game, right? The end game is trying to understand, is general relativity correct? What's happening outside a black hole? Is it launching these jets? How does this all work? So we do computer simulations. In this case, this is some of the work of my group, but other groups, are working on this, of course, as well. We have many groups in the whole EHT team. But typically what we do is we build a computer model of a black hole. So what you're looking at is a computer simulation where the black hole's here in the middle, and there's sort of a donut that you're looking at a slice of material, which is wrapped around the black hole, and it's seated within black magnetic field lines. And then we let it go. Now to look at the scale, this is already about, this RG unit is basically the event horizon size. So this is already 1,000 gravitational radii, but we have such high resolution that we can also see what's happening at very small scales. And then we can even expand it, and we try to, so we start to see turbulence is generated, magnetic fields are amplified, they get pulled in, you end up launching these jets. And now we can actually follow these jets in our simulations out to scales that are really physical, like out to the scales where the black hole jets are impacting their environment. But the problem is, how do we know this is right? So we make a simulation. There's no really like light in these simulations. We have to put the light in as a separate model later, and that's where a lot of our uncertainty comes in. I won't go into the technical details about that. I'll just give you a little sense of it. Why do we have so much trouble connecting the image that we see to understanding, for instance, these jets? So this is a volume rendering of what happens when you have a simulation like this. You get here's the blue shows you the disk of stuff falling in, and red is showing you these jets that are being launched. But when we look with the Event Horizon Telescope, we lose most of this information because, number one, we've picked our planet as kind of the size scale, which means we're looking at tiny scales. So we're really only able to see things that are very close to the black hole. And secondly, we pick a frequency that is also sort of like high frequencies tend to focus things closer to the more extreme regions near the black hole. So to give you an idea, this is actually a movie that's showing you what happens when you do general relativistic, ray tracing. What would you see if you looked at a system with the disk and the jets from one of our simulations at low radio frequencies, you would see, a lot of stuff. But as we go to higher and higher radio frequencies, like the event horizon, and then we have the telescope size that we have, we're basically only able to see this region that is where all the light is being bent. And so we don't even know if the light is coming from the disk or the jet at this point. So, and in the case of Sagittarius Star, we're not even sure that there are jets. So this is a very difficult problem at the moment that we're trying to now interpret our results. And also eventually we want to like bring back the jets and understand the big picture. So our workhorse is these kinds of what we call general relativistic magnetohydrodynamical simulations. And the image, we have this sparse sampling, as I said. So we end up with something that's kind of fuzzy and blurry. And somehow within this image, which is this simulation here, blurred to our resolution, we're trying to reconstruct the part of the image here that doesn't change is this photon ring, which is where the photons are basically bent and tracing just outside the event horizon, which is telling you the size of the black hole and can give you information about the spin potentially of the black hole. That's the part that's general relativity. But then you have all of this astrophysical fluff, which is basically, around the black hole. And then you're seeing a movie, but mostly so far what we've only worked with is snapshots, which makes it a lot harder to actually make the, we're moving towards dynamics. I'll talk about that later. But the first thing we needed to do was to be able to fit a snapshot image. So what we do is we make many simulations. And for the 2019 paper, which was on M87, which was the first one, you can see that, we've got like 43 full computer simulations. So very computationally expensive, terabytes of data. We made 60,000 snapshot images. And then each image, we try to say, okay, there's some statistical probability. Each image is a little bit different. So we have to correct and figure out what is the bias between what happens with the astrophysics kind of sloshing around versus the probability that we have this ring in the center. And that's really where we get a lot of our uncertainties. So for M87, we could really say only that within about 20%, the shape and the size was consistent with relativity, general relativity. We see this asymmetric ring that tells us something about, the Doppler boosting, that light is coming towards us at the bottom, moving probably near the speed of light near the black hole. So that gives us some idea of the geometry. In 2021, we actually published some polarization. So that tells us there are very strong magnetic fields. And that sort of didn't surprise us because we need strong magnetic fields to get these big magnetic jets, but it's good to see them and it gives us some information. But we really cannot at the moment connect the image from EHT to these jets. And we would need smaller baselines to give us access to the larger structure. We would need more telescopes in the array. But we have this other black hole, like I was saying, which is not in this active state. And what is that doing? So we did this once later. The reason we did it after M87 is because it was actually much more difficult to analyze because it's a smaller black hole and it's kind of flickering all the time. On the other hand, there was a Nobel Prize given particularly to the groups of Genzel and Guess, who for the last decades have been looking at actual movement of stars around the black hole in the infrared. So they were able to say really high precisely what is the mass and what is the distance to this black hole, which removes a lot of our uncertainty that we have for a very distant black hole like M87 star. And so at the end of the day, there's the part where we're trying to understand GR, and we can say that general relativity, given the mass and the distance that we know, makes a prediction of how big on the sky the ring should be. And lo and behold, the rings are basically about the right size. So we can, but our error bars are on the order of 10 to 17%. 10 for Sagittarius Star because we have better information going in than M87, where it's 17%. If we want to improve this, there's two things we need to improve. One would be the telescope precision, so more sampling, or we need to understand the physics better because we're trying to separate out the astrophysics from the GR. So that's where the simulations come in. Now, this was 2022. We had several years in between this, which during the pandemic we were working on. And we also had to deal with figuring out new algorithms because this black hole was changing on the sky at the same time we were integrating the light, which makes it very difficult. But we had other information that we didn't have for M87, which is flickering. This is the black hole, Sagittarius star, flickering in the X-rays. And here it's flickering in the infrared. And this flaring, it's very similar to the sun. So if you look at a picture of the sun, a movie of the sun and the solar corona, you see this flickering and this turbulence and this flaring. We're basically seeing exactly the same thing, but in a more extreme conditions right outside a black hole, which is pretty crazy. But we now have the kinds of computer simulations where we can, this is a simulation with a black hole. So you see the size of the event horizon, and we're able to create, these vortices and these regions where you get like magnetic reconnection, and to try to understand the variability in the flickering. And that's where a lot of the work is going at the moment. But to give you some idea of the last papers, because we had many more constraints and we also had more time, we had hundreds of more simulations to add. We had millions of images, which is just petabyte of data. And this little movie here will show you our constraints. So we looked at the size and the shape of the images. We could rule out some models. Then we could rule out more models by using this infrared and the X-ray information that we had by fitting the spectra. And then we also have variability. And so starting with this 200 core set, the size didn't really remove many because we knew the size, what it should be, and we kind of got that right. But the shape ruled out a lot of the models. Then on top of it, with multi-wavelength, we got down to 4 models, and that's by basically trying to fit the spectrum from the millimeter, infrared, and the X-ray. Here's a model that passes. Here's a model that fails because it's going over the data, basically. And finally, we get down to just 2 models that seem to be consistent, and that gives us more information. So we can actually say things about the spin, the inclination of the black hole, about the relationship between the radiating particles, that the electrons and the ions are not strongly coupled. I won't go into a lot of the details about that. But what's weird is that there's a very strong magnetic field. And basically, they seem actually, M87 star and Sagittarius star seem very similar, although they're operating at very different power scales. And weirdly, everything seems to point from our theoretical knowledge that Sagittarius star should have jets. And yet we don't see jets. So the question is, are the jets there, but they're just kind of hard to see in this complicated background of the galactic center? Is it because the particle acceleration in these jets is different? So there's a lot of work now trying to understand, are our theories wrong? Do we think Sagittarius star should have a jet, but maybe it really doesn't have a jet and we've got something wrong there? There's a lot going on. So we're trying to do a lot of work to interpret Sagittarius star and, whether or not it has a jet or not, and trying to understand these flares. And I know I'm almost up to time, so I'm thinking, I can jump to almost the end. I just want to say, basically I'm going to skip this, but this tells a little bit about the fact why we don't know which model is correct. And that has to do with the fact of some degeneracies in our model, that we can have very different black holes. Each one of these are quite different black hole model, but the final image will look quite similar. That's called model degeneracy. And so we're trying to basically now look at the larger scales and say, okay, so we can make an image, but we also know that the jets from M87, this is an actual movie of the jets, have a certain shape. The black hole's down here at the bottom, but our computer simulations have to also be able to, in this case, reproduce things like the opening angle and the shape of the jets. And here's showing you the data, and here's the model in red. And, we're getting okay with the dynamics, but there's a lot that we still need to do. And in fact, in 2017, and this is part of what I do in the collaboration, is every time we look at a black hole, here's the famous image. We also looked at the system with radio telescopes with different size arrays, so they could look at larger scales and see the entire jets. We looked in the X-rays with Hubble, Chandra's another X-ray, and then even the gamma rays. And so we have much more information than just the image. And we have a full spectrum. So this is the amount of light coming out as a function of frequency. And in that sense, we only have one data point from the EHT, but we have to make models that can fit, all of this and the shape. That starts to become very constraining. So the future is that we've got lots of systems where we can see the jets, but we cannot see the black holes. So we're going to be using these to actually study different systems in the coming years. We're going to be trying to kind of map what's happening from the event horizon region out to the larger scales in the jets. And we're hoping that if we build new telescopes, we'll be able to actually start to make images that look more like this, where we'll have the shadow scale, but we'll also be able to start connecting this to the jets and trying to understand these questions that I was talking about. So here is sort of showing you that we're starting to think ahead. How can we make the array bigger? And in yellow, you see the current array. And in blue, these are possible sites where we might be able to start including new telescopes. Either they exist, but they aren't up to spec and we have to like refurbish them. Or in the case of here in Namibia, this is the one I want to focus on. This is a great place to put a new telescope because you can see it sort of puts a telescope in a part of the Earth that we don't have one at the moment in the millimeter. And then we can create all these new baselines. And it actually makes a huge difference, even though it's only one single telescope. And in fact, in the Netherlands, this is the one we just got funding. We just found out before the holidays that we got funding to build this. So in the coming years, we're going to be adding to the array. And you'll start to see this happening throughout the world, I think, in the coming decades. I'm going to skip over this, just saying that it makes better images. There are many black holes in the universe. We know of millions of them. So if we can understand a few really well, the idea is that we can start to understand, all of these black holes that we're seeing in different wavelengths and start to put the big picture together. So there's a real trying to understand cosmology and how the universe, evolved is a big part of this. But I'm going to leave it at that. It was a bit of a whirlwind tour, and I hope that some of you have some questions. But I think, the main takeaway of this is that if you think about where we live today, it's been a crazy 110 years, going from not even knowing these things existed to finding them, seeing them. And black holes are really important, so we would like to understand them. And there's a lot of ideas about how to keep studying them, but the Event Horizon Telescope, or EHT, plays a really important role. So I think that's it. So let's see if we've got some questions.
Thank you, madam, for your wonderful and excellent lecture. So we have got few questions in the inbox. So if you allow, we can start our discussion session. So first question, what will happen when two black holes collide?
So when two black holes collide, well, usually, one of the things that happens, just like anything in astrophysics, is that they have angular momentum. Most things have angular momentum. So, if you think about our sun has planets orbiting around it, and the planets don't fall in, right? Because even though the sun is pulling it towards it, you have to lose angular momentum in order to get a smaller orbit. So what happens is if two galaxies collide and then you have two black holes, this is what we also see with gravitational waves with LIGO and Virgo, is that the black holes will basically circle each other, and it can take a very long time, but eventually they will collide and they will merge. There'll be this big, gravitational wave burst, which is called like the chirp, that people are finding now with the gravitational wave detectors. Now the small black holes are already being seen merging into one bigger black hole, and basically all the mass goes into this black hole. You lose a little bit of energy from the gravitational waves. And then the people are measuring now, the initial masses, the spins, and then the final mass and the spins. For supermassive black holes, because they're bigger, the frequency is different than what you can see with LIGO Virgo. So actually, there are missions called like LISA, which should be in space in the coming decade, and then people will be able to start looking at these mergers there. So they grow by merging, but they also grow by just capturing material. If you throw a star into a black hole, that's how you grow the star, by one stellar mass as well.
Okay, madam, thank you. We have another question. Question is, you said that black holes spend most of their time being rather harmless. So then when and how it become harmful?
So that's a great question, and that's part of what we're trying to understand, by looking very close to the event horizon. Basically, it's just a matter of luck for the black hole, whether or not it manages to capture some material enough to basically activate it, because the efficiency of mass energy conversion. So if you imagine, Einstein said E equals mc squared, right? Energy is equal to mass times the speed of light squared. So if you have a perfectly efficient process, then if you would have 100% of the mass get converted into energy. Nuclear fusion, which is basically the best thing that we could even think about doing on Earth, but that's how stars are powered, is somewhere on the order of, like, what is it? I think about 7% or something. I think that's about right, or even less, but it's about 10 to 7. No, it's even less than that. I think it's 0.07%, but it's pretty low efficiency. And black holes will be on the order of 10 to even spinning black holes up to 40-ish, percent efficiency at mass conversion. So what you just need is you need stuff to fall into a black hole to make it active. And we see, for instance, these things called tidal disruption events, which is when a previously dormant black hole, similar to our, galactic centers like Sagittarius star, manages to get a star. A star is unlucky enough, probably with its planets and everybody on them, falls into the black hole, and it activates, and the black hole becomes active for kind of a very temporary period of time, and then it goes away. For the more sustained things, like what we see in M87 star, with these huge jets that have to take a long time, we think that there's sort of a direct stream of gas maybe coming in from like the outer, part of the galaxy where when collisions are colliding, you lose angular momentum, stuff falls in and powers the black hole for some period of time. And the black hole can play a role in pushing that stuff out and stopping its own feeding source. So that's what I mean also by feedback cycles. In our own galaxy, we have some evidence, quite a lot of evidence actually, that our black hole was active in the past. And we think that probably it was due to either capturing a star for the small bursts of activity, or we see evidence of a kind of dormant disk at large distances that is not feeding the black hole at the moment, but probably in the past it used to.
Thank you, madam. We have a question in comment section. I can add the question. So, can black hole grow? And if it's possible, then is it possible for a black hole to eat an entire galaxy?
So I don't know if you caught the beginning of the talk, but I sort of mentioned a little bit about that. So, I mean, I think the last question answered about the fact, yes, black holes grow. As long as anything falls into them, they will grow, or two black holes can merge, and that's how they grow. To eat an entire galaxy, right? Again, I was saying at the beginning of the talk that a black hole can only grab material out to a specific radius around it, which is actually pretty small compared to the galaxy. It's something like 10 to the minus 5 times smaller. So if you imagine the black hole in the center of a galaxy would never be able to eat the entire galaxy. It's just too small on the scale of the galaxy. So I hope that's a bit reassuring. And you could imagine that sometime, what could happen at some point is that for dwarf galaxies, there's evidence that you can have big black holes inside a small galaxy. It never eats the entire galaxy, but it has more of an effect. Like when it becomes active, it can actually blow the gas out of the galaxy and sort of stop star formation and do interesting things. So depending on the ratio between the black hole and its galaxy, it can be more powerful. Yeah.
Now, this may be the last question. So what is the black hole jets?
Sorry, what is the question?
Black hole jets.
What is the question about them? I can't see it on my screen, so.
Okay, I can send in the chat.
Mm-hmm.
Can you see in the chat?
I'm seeing the chat, but I'm not seeing in the comments. Somehow I don't see that one. So is the question what's inside them? Or?
Jets about black hole jets.
Yeah, but what about them? I don't understand what the question is about the jets.
Okay, madam. So thank you. It's a very exciting lecture. Actually, many information you have showed in your lecture, and I think many of our students and viewers will fall in love in this astrophysics and in this high energy physics group. So
I found the question now in the chat, not in the comments. Do you want me to answer it really quickly? I mean, what is the jet? Well, that's a great question in the sense that, we see them, right? I showed pictures of them. So we know just from the fact that they're emitting synchrotron light that they have to contain relativistic particles. That means particles that are moving almost near the speed of light. And they have to contain strong magnetic fields. because that's how this light is made. But they also make other kinds of light. They make light from particle scattering, they accelerate particles. There's actually a big debate what exactly is inside them. Are they only made up of light particles like electrons, or do you actually have very heavy particles, which we call like ions? It's a big question, right? Because if the jets are made significantly of these heavier particles, it takes a lot more energy to push them up to relativistic speeds. And so that would mean that the black hole would need to be more powerful. So it changes the models depending, on what's inside the jets, but also the black hole, the effect it will have on its environment. You can imagine that if you're taking a bunch of particles, and if they're very light and fluffy, you accelerate them up to relativistic speeds and you smash them into the rest of the galaxy, they'll have an effect. But if you have heavy particles, what we call the ram pressure, just the amount of weight being smashed into the galaxy will be a lot more. So the effect will be a lot more. So in fact, physicists and an astrophysicist like me, I mean, we spend a lot of our time modeling, debating, arguing. And in fact, that's one of the free parameters that we have in our models at the moment when we try to model the EHT. So it will be combining EHT data with other facilities and trying to fit this whole spectrum, trying to fit the variability that will try to be able to answer this in the coming years. But sorry, I didn't understand the question because I just couldn't see it, but now I got it.
Thank you, madam. So one last question. So student, I think you have student from India. So if a student from Bangladesh want to join your group or this type of huge group, so what student need to do? Because here there is no that type of huge telescope, and I don't know there is a collaboration that much.
Yeah.
So if student want to join there, so what the
Yeah,
basic
so we
criteria?
actually, here in Amsterdam, we have a lot of Indian students. I don't think we've had a student from Bangladesh. We've had students from Nepal. And so generally what happens is, so we have in our program, it's a bit different than say like the United States or some other ones, but we have bachelor's, then master's are separate degrees, and then the PhD is separate even from that. So the master's program here is basically free for European students because they're paying, or not entirely free, but it's quite cheap for European students because they pay the taxes. But for people outside the EU, the tuition is actually quite high. There are some scholarships though that you can apply for. But the best thing that I would advise is, well, usually what happens is the students coming from India and nearby, they do their master's, often like an integrated bachelor's master's program in India, but they study. They can do a lot of things remotely with like projects and internships. So I would say if you're interested in this kind of thing, if you can't find somebody local who's working on it, you can contact, there are plenty of professors in India, for instance, who are working on this. I don't know in Bangladesh if there's people working on black holes, but you can contact professors and say, I need to learn some of these things. A lot of the codes and the data and things are actually all on GitHub. They're on like publicly available. So there's even tutorials that you can go and learn how to run some of these programs. And you can do a lot of things almost like a supervised learning. We have in summers here, we have a program called Aspire, ASPIRE. You can find information about this on the website for University of Amsterdam. And there we basically take applications for usually master's level students to come for the summer, and we pay for everything. So it's a nice thing. You get to come to the Netherlands and work for 8 to 10 weeks in a research group. So you can apply for that, for instance, and then you can come and then you get some valuable experience. And then, once you have some experience, you apply. So, I mean, just to make you feel maybe good, we're actually applying. I mean, we're hiring PhD students right now, and we have 6 positions, and we're doing interviews. And for the positions that me and somebody else are hiring, I think sort of 75% of our candidates are actually coming from India this time, because there's such a good, programs there in mathematics and physics and so on. So it's actually quite common to get involved in this. And so I would just say, if you're interested, get involved.
Okay, madam. Thank you. So thanks again for giving us this opportunity, and hopefully in near future we can arrange another webinar and face to face, as you have mentioned in the earlier when you started that you want to visit our country and our university. I'll be very excited, and our student will be very excited when you will meet us. So thanks again.
I hope to someday come. I like to see new parts of the world, and thank you so much for the invitation. I hope that the level was okay and that the students got something out of it.
Okay, madam. Thanks. Bye for today.